Hello everyone, welcome to this special video. Before we dive into the spectacular question of how stars die, I have 3 quick requests. Please like this video right now, subscribe to the channel if you haven't already, and share it with your friends if you find it fascinating. Now, let's leave earthly concerns behind for a bit, and embark on a cosmic journey to discover what happens when a star runs out of fuel and meets its inevitable end. What does dying mean for a star? We often talk about the death of a star in a metaphorical sense. Of course, stars aren't alive as organisms are, but they do have a lifespan. They form, maintain a balance of forces for millions or billions of years, and ultimately undergo dramatic changes when they exhaust their nuclear fuel. A star's life is spent mostly in hydrostatic equilibrium, where the outward pressure from nuclear fusion balances the inward pull of gravity. Eventually, this equilibrium collapses when the star can no longer maintain enough fusion in its core. But the exact outcome differs significantly depending on the star's mass, which is the key factor in determining whether it will fade quietly or explode spectacularly. If you've ever looked at the night sky and imagined that those tiny lights are unchanging, you might be amazed at how dynamic stars really are. Let's explore the different mass categories of stars and how each type comes to its cosmic finale. The smallest, red dwarfs, and their incredible lifespans. At the lowest end of the stellar mass spectrum, we have red dwarfs, stars that can be as little as 1/10 the mass of the Sun, or slightly more, up to about half a solar mass. They shine relatively faintly and have a lower surface temperature, appearing red to our instruments. Interestingly, red dwarfs are thought to be the most common type of star in the galaxy, even though they're too dim to be prominent to the naked eye from Earth, unless very close. Red dwarfs have extremely long lifespans, possibly hundreds of billions or even trillions of years. The reason is that they consume their hydrogen fuel slowly and often have fully convective interiors, which allows fresh hydrogen from outer layers to continually move into the core region. Because the universe is only about 13.8 billion years old, no red dwarf has yet reached a final end stage in real observation. Theorists predict that eventually, after unimaginably long times, a red dwarf might become a white dwarf once all hydrogen is spent. But since none have died yet, the universe is too young, these stars are often deemed quasi-immortal on current cosmic timescales. Sun-like stars, from main sequence to red giant and white dwarf, moving up to the more familiar class of stars, such as our Sun. These mid-mass stars, roughly 0.5 to 8 times the mass of the Sun, spend most of their lifetime, billions of years, fusing hydrogen into helium in their cores. This stable state is known as the main sequence, but eventually, hydrogen in the core depletes. The core contracts and heats, and the outer layers expand significantly. The star enters the red giant phase. In our Sun's case, this is expected to happen in about 5 billion years, possibly enveloping Mercury and Venus, and quite possibly Earth's orbit, rendering our planet uninhabitable or even swallowed. The star's surface cools as it expands, giving it a reddish hue, but the inner regions can fuse helium or heavier elements. After some time as a red giant, the star's outer layers become unstable and are ejected into space, forming a beautiful planetary nebula. The core that remains shrinks into a white dwarf, a small, dense remnant, often Earth-sized yet with nearly the Sun's mass. White dwarfs no longer fuse elements. They simply cool and fade over extraordinarily long periods. Eventually, in theoretical timescales far exceeding the age of the universe, a white dwarf could become a black dwarf. But none exist yet because even the oldest white dwarfs haven't had enough time to cool that far. This process, from red giant to white dwarf, is the typical fate for stars akin to the Sun. Although less dramatic than Titanic explosions, it's still a significant transformation. The ejected planetary nebula enriches interstellar space with elements the star formed, contributing to the cosmic supply of heavier elements. Massive stars, spectacular supernovae, neutron stars, and black holes. Now for the real cosmic fireworks. Massive stars, those more than about 8 times the mass of the Sun, can reach 10, 20, even 50 or more solar masses. These giants live fast and die young, often only a few million years. They fuse hydrogen, then helium, then progress to heavier nuclei, carbon, neon, oxygen, silicon, etc., layering like an onion. When they eventually build up an iron core, trouble arises. Iron fusion doesn't produce net energy, it consumes it. Without the energy to support the star's weight, the core collapses abruptly, setting off a gargantuan explosion known as a core collapse supernova, Type 2. A supernova can outshine an entire galaxy for a brief period, releasing a flood of heavier elements into surrounding space. These newly forged elements, from iron, nickel to many other heavier nuclei, are key to forming rocky planets and living organisms. In effect, the death of a massive star seeds the cosmos with the building blocks for new generations of stars and potentially life. What remains after the explosion depends on the leftover core mass. If it's still quite heavy, the star can become a neutron star, an incredibly dense object only a few tens of kilometers across but containing more mass than the Sun. If it's even heavier, gravitational collapse proceeds, forming a black hole, where gravity is so extreme that not even light escapes. These two outcomes rank among the most exotic phenomena in astronomy. The special case of Type Ia supernovae. Not all supernovae form from collapsing massive stars. Another route is the Type Ia supernova, which occurs in a binary system featuring a white dwarf. The white dwarf siphons material from its companion, steadily increasing its mass. Once it exceeds the Chandrasekhar limit, or 1.4 solar masses, a runaway thermonuclear reaction ignites, and the white dwarf is obliterated in a powerful explosion. Type Ia supernovae are valuable standard candles because they typically reach a consistent peak brightness, letting astronomers measure cosmic distances with relatively high precision. Our Sun's future: a red giant, then a white dwarf. When people ask, what about the Sun? Well, it's a mid-sized star. Astronomers estimate it's about halfway through its 10 billion-year main sequence life. In roughly 5 billion years, the Sun will deplete its core hydrogen, expand into a red giant, and quite possibly engulf Earth. After shedding its outer layers as a planetary nebula, the leftover core will settle into a white dwarf, slowly cooling across eons. From a human perspective, this time frame is unimaginably long, but in cosmic terms, it's just another step in the life cycle of a star. Life on Earth, if it's still here, would not survive these changes, of course. Cosmic recycling and the formation of heavier elements. The reason star death is so essential to the universe is that it's basically cosmic recycling. Massive supernovae, along with other final stages of stellar evolution, release heavier elements formed in stellar cores or during explosive nucleosynthesis. Those elements spread into interstellar clouds, from which new stars and planetary systems can form. Our own bodies contain atoms literally forged in ancient stars that died billions of years ago. This highlights that we are, in a literal sense, made of star stuff, as Carl Sagan famously put it. Thus, the dramatic ends of stars serve a crucial role. They create and distribute the chemical diversity that eventually becomes life, planets, and everything we see in the cosmos. Without supernova explosions and stellar ejections, the universe would be mostly hydrogen and helium, lacking the complexity necessary to host advanced planetary systems or biology. Summarizing the fate of different stars. Let's recap these varied destinies. Red dwarfs burn hydrogen slowly, can live for trillions of years, eventually fade to presumed white dwarfs, but the universe is too young to confirm any have done so. And sun-like stars spend billions of years in main sequence hydrogen fusion, expand into red giants after hydrogen is used up, shed outer layers forming a planetary nebula, leaving behind a white dwarf. Supermassive stars burn through successive shells of elements culminating in iron. Lack of net energy production leads to core collapse and a Type 2 supernova. The core's remnant becomes a neutron star or black hole, depending on mass. In each scenario, the star's death recycles matter and energy, fueling cosmic evolution. Some star types show additional nuance, binary star interactions, different metallicities, etc. But the overarching theme is that mass is the prime determinant of a star's eventual end. Observing stellar demises, although we can't witness a single star's entire life cycle in real time, these processes often take millions or billions of years. We gather snapshots from the universe at different stages. Astronomers observe supernova events in distant galaxies, detect neutrinos from core collapse, measure pulsars, rotating neutron stars, or track exoplanetary nebulas. Even gravitational waves from neutron star or black hole mergers provide clues to stellar endpoints. Each piece of data builds a picture of how stars live and die, refining our theories about the cosmos. Conclusion: an end that sparks new beginnings. While calling it a death might sound grim, the end of a star is anything but final in a cosmic sense. The material cast off, whether in gentle outflows or violent supernova blasts, is the seed material for new star formation, new solar systems, and the eventual possibility of life. Our own planetary system is shaped by elements from ancient stars that long ago ended their journeys in spectacular ways. So when you look up at the night sky, remember, each of those lights is undergoing a life cycle far beyond our timescales, culminating in a finale that might be sedate, like becoming a white dwarf, or explosively brilliant, supernova. The universe thrives on this continuing cycle of stellar births and deaths. Thank you so much for joining me on this cosmic tour of star deaths. If you enjoyed the video, please remember to like, subscribe, and share it.